Hello everyone, welcome to another lecture of control systems. In today's lecture, we are going to see the step response for a critically damped system. So what is a critically damped system? So we have seen in the previous video, a critically damped system is a system for which your damping ratio zeta is equal to 1. So when zeta is equal to 1, you have a critically damped system. So we will see what is the response of that system when your input is a unit step signal. So that is your step response. So when you have your input signal to be a step signal, you get a step response. And in terms of the Laplace transform, I can write my step signal to be R of S is equal to 1 by S. Good. So now I have for my critical damping zeta equal to 1, the transfer function C of S by R of S is given by omega n square divided by S plus omega n the whole square. Good. So now putting R of S is equal to 1 by S, I get the modified function or the modified system function output C of S to be omega n square divided by S into S plus omega n square, which is in a factorizable form. So I am going to do the same three steps that I have been doing for your previous two damping case of zeta equal to 0 and zeta equal to 1. Those are, I'm gonna do the partial fraction expansion first, then compute these partial fraction coefficients A, B and C. Then I'm going to apply my inverse Laplace transform to get my C of t, which is your step response since your input signal was a step signal. Good. So now how do I simplify this partial fraction expansion to get my A, B, C? For that I follow the three steps. First of which is I multiply my RHS and LHS with the denominator in your LHS. So that is going to be S into S plus omega n the whole square. So when I do that, what I'm going to get is I'm going to have S into S plus omega n square multiplying on all with all the fractions, and that's going to cancel out some of the terms as shown here. Yes, so what do we have? So now the next step in your partial fraction solving is to write the simplified expression, and then you equate the coefficients on the right hand side and the left hand side for the powers of s, starting from s square till s to the power 0. So when I am doing this, so this is my simplified expression, and I'm going to equate the coefficients. So when I do that, I'm going to end up getting three simultaneous equations, and I can solve for three variables from three equations. So it is a well-known problem. So I can solve them using a linear system of simultaneous equation solving. So let us see what are those three equations that I get by equating my S square term coefficients. So on the left hand side, I don't have any coefficients for S square or S to the power 1. I just have an omega n square, and that can be considered to be a constant, and that is my equates to my S to the power 0 term, right? So that is your omega n square. And on seeing these three equations, I get my value of A from the third equation, because the third equation says A omega n square equal to omega n square, and then we get our B and C. Good. So now I can write this partial fraction. I can write this partial fraction as 1 by S minus 1 by S plus omega n and minus omega n and S plus omega n square. So those are my A, B and C value. And now do I have a direct inverse formula? So I need to check whether I have my direct inverse Laplace formula. And if I look at this, I can see that I have 1 by S and I have 1 by S plus omega n, both of which we have already seen and both of which have a direct formula. But I am only now interested in my third fraction which is 1 by s plus omega n the whole square. So if I look at that fraction, yes, I do have an inverse formula associated with that, which is given by 1 by s plus a the whole square is equal to t e to the power of minus at. So applying these inverse formulas, I get my c of t to be 1 minus e to the power of minus omega nt into 1 plus omega nt. So what is this response looks like when you plot it against the time axis? So C of t versus t is gonna give a linear plus a constant response, but not an oscillatory response. So I don't see any oscillatory behavior here. I just see the first part to be linear and the next part to be my constant. Good. So that is your step response when your damping ratio is equal to 1 or your critical damping. Next, let's come to the root characteristics of an underdamped system where your damping ratio zeta is between 0 and 1. So now my transfer function C of s by R of s is in its original form, which is omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared. So now when I'm talking about the root characteristics, I'm just talking about the step response also, because that is what we have been saying for all these cases. And let us take here also to understand our underdamping system. We will take the zeta to be between 0 and 1 and also our input signal to be our step signal. So which means my step signal R of s input in Laplace transform is 1 by s. So I'm going to apply that here, and then I'm going to use the partial fraction expansion that I always use to solve these kind of s fractions, right? Fractions in our s plane. So now as you can see, my characteristic polynomial is in a non-factorizable form. So my partial fraction expansion is a and bs plus c. So that is what you use for non-factorizable polynomials in your denominator. Then the solutions to these partial fraction expansion is the same as for non-factorizable and factorizable. So which means I'm going to solve this in the same way I did it for previous factorizable partial fractions. What is that? That is, my first step is going to be multiplying my right hand side and my left hand side with the denominator of my LHS, and that is going to be s into s square plus 2 zeta omega ns plus omega n square, and that is going to be this. Good. And that is going to simplify this fractional expression into a non-fractional form. So when I do this multiplication of my denominator, what happens is what was before my fractional expression is now just a linear equation, right? So it is just an equation. It's not a linear equation, but it is just a non-fractional equation. And the next step is going to be equating the coefficients of s square, s to the power of 1 and s to the power of 0, and then you compute the values of a, b and c from these three simultaneous equations. Good. So what do I have? On my left hand side, I don't have any s square coefficients and s to the power 1 coefficients, which was the same in all the cases prior to this. So that is going to have 0 on my left hand side, but on right hand side I'm going to have something in this form, a plus b and 2a zeta omega n plus c, and my s to the power of 0 term is equal to this. Omega n square is equal to a omega n square. A equal to 1, b equal to minus 1, and my c is going to be equal to minus 2 zeta omega n. Done. So these are the three values that I have, and now I can apply them to the partial fraction expansion, and that is going to come as, this is going to come as 1 by s plus minus 1. I'm just going to plug in these values for a, b and c and see what I get. I get something like this, but here the next step is something which is not very straightforward. So that is, how do I solve this? What is the inverse Laplace? So I need to do my inverse in order to get the step response C of t. And then what I have is the closest formula that I have where I can apply my inverse is this: s plus a divided by s plus a the whole square plus b square, and that is going to be equal to e to the power of minus at cos bt. Then you have b divided by s plus a the whole square plus b square, and that is going to be e to the power of minus at sine bt. So now I'm looking at a partial fraction on, I'm looking at a fraction on my right hand side, which is the outcome of my partial fraction expansion, and then I have to convert that fraction into something where I can apply my inverse and convert it into this form of either e to the power of minus at cos bt or e to the power of minus at sine bt. So which means I need to make some switching, substitutions and alterations to that fraction. So I start with this, so where I take my s plus 2 zeta omega n, and then I split them into s plus zeta omega n and plus omega n. So when I do this, then I'll write these fractions separate. Then I'm going to get something like this. This is the first part of the fraction, which is s plus zeta omega n divided by s square plus 2 zeta omega ns plus omega n square. So now I'm looking to convert that fraction into this form, s plus a divided by s plus a the whole square plus b square. And I can do that because I know what is my a. So my a is gonna be zeta omega n. So I can take that numerator and I can compare. So that is gonna be zeta omega n, and this is gonna be s plus a divided by s plus a the whole square plus b square. Good. So how do I now convert that fraction into this form? So that is gonna be s square plus 2 zeta omega ns plus zeta square omega n square divided by what will happen. So how do I correlate this 1 and 2? So what I need to do is I need to take this 2 and then make that 1 look like 2 plus some extra terms. That is going to be my b square, right? So I want to do that s plus a the whole square, and when I do that, I'm going to get this plus or minus zeta square omega n square. So I'm just going to show it to you, so it is, you better understand, when I write this. Okay, see, now what I've done is, to that 1 I have added a plus zeta square omega n square, and then I've taken a minus zeta square omega n square, because that is going to basically have no effect on that polynomial. But now what I can do is I can write in this form. I can write it as s plus zeta omega n the whole square plus omega n square into 1 minus zeta square. And I know that my omega n square into 1 minus zeta square is nothing but omega d square, right? So that is going to be just my omega d. So omega d is, I can write this to be s plus zeta omega n divided by s plus zeta omega n the whole square plus wd square. Now this is in this form. So I have the second fraction already in that form of s plus a divided by s plus a the whole square plus b square. But my second fraction, if I multiply by omega d and divide it by omega d, then I can also convert that second fraction into b divided by s plus a the whole square into, right? So I can do these two substitutions. I have done the first one previously, and for the second one I am just multiplying and dividing it by omega d, and then I am able to apply my inverse Laplace transform. I'm going to call this e to the power of minus at cos bt and e to the power of minus at sine bt. And what is my a and b? A is my zeta omega n and B is my omega d. I'm going to put that in this equation, and that is going to come as Ct is equal to minus zeta omega n cos omega dt minus zeta omega n divided by omega d minus into sine omega dt. Good. This is the simplified expression. I'm taking my e to the power of minus zeta omega n common, and then I'm gonna just write this in this manner. Okay, so my omega d is that. So now what I do is I expand that omega d, right? I written as omega n into root of omega 1 minus zeta square. That is my damping frequency. And now I can, what I can do is I can again simplify. So the idea is to introduce some more simplification, because I can represent this in a much simpler form, and you don't have to necessarily do that if you ask me, because you can stop at Ct is equal to that long expression on the right hand side. But it is recommended because that is the formulas in your Nagrath and Gopal book, and also in some of the reference books which is out there. They go on to simplify it further and represent a very compact step response for your underdamped system. And I said, as I've told you before, underdamped system is the most important system. Every system, or you can say like 90% of the system out there in the real world, use this underdamping. So they work with the damping ratio between 0 to 1. That allows them the flexibility, scalability for more control on their systems in terms of design, performance, and efficiency. So they use this system a lot. So that is why we go further and simplify it. And here we are applying this Pythagoras theorem. So we are applying the right-handed triangle. Right angle triangle for my zeta and root of 1 minus zeta square, and I'm introducing that to be my cos theta and sine theta. So my cos theta is equal to zeta and my sine theta is equal to root of 1 minus zeta square, and that is going to simplify the terms within the bracket to be cos A sine B plus sine A cos B, and that is, or you can write it as sine A cos B and cos A sine B, and that is going to be equal to sine A plus B. So in this case, I'm going to write this as sine omega dt plus theta, and that is your simplified expression. So here what I'm having is I'm having a phase. I'm introducing omega dt plus theta, and you all know that your omega d is the frequency component and your theta is the phase. And now I have converted this, our damping, into a phase term for our step response. So which means I vary the phase. I can have a different phase, linear phase, non-linear phase, lead phase, lag phase. So plenty of designs are available on this, but that is the most simplified step response for your underdamped system. And your how the response graph is going to look like is it's going to have linear behavior, oscillatory behavior, and a constant behavior. Good. So that is your step response graph, and that is your underdamping system. It is a very important system, and it's very good that you understand how the step response works and what are the characteristics of the roots of your underdamped system. Now let's do a typical numerical that comes from these areas for your exam. So you'll be given a control system which is in this manner. So this is C of S is your output, R of S is the input, and then you have the system function G of S, which is given by 100 divided by S into S plus 2. Then you have your feedback function given by 0.1 S plus 1. Good. So find step response. So the question is to find the step response. So when they say you have to find the step response, which means your input signal is a step signal. So now I can write which means my R of S is equal to 1 by S. So, but before I do that, let us see what my transfer function will be for this system. So that's going to be g of s divided by 1 plus g of s into h of s, and this is equal to 100 divided by s into s plus 2. Good. And that is going to this one into 0.1 s plus 1, and then 100 divided by s square plus 2s plus 10s plus 100. So this is how it simplifies to, and what you have in the denominator is your characteristic polynomial. And now I need to, what is the question is to find my step response, which means I need to compute the roots, or I need to do the simplification and get my C of t. So how do I get my C of t? I start with doing, okay, let me first, I have to check whether what is the damping ratio. So the damping ratio value will tell me what type of a system I am having, whether it is a critically damped, it is an underdamped system, or it is an undamped system, or it is an overdamped system, right? So on computing, I can see, I can substitute that denominator. I can get my omega n square equal to 100, and then my 2 zeta omega n is equal to 12. Then we have my zeta to be between 0 and 1, right? So that means we have an underdamped system. So zeta is equal to 12 by 20, so which is my 0 point something, which is less than 1. So that is your underdamped system. And now I am going to show you two methods on how to solve this. You can do it either using your shortcut method, or you can do using your long method. So depending on how you are looking at. So if you're solving a detailed question for 10 marks, you may have to show on elaborate on all the steps. But if you are attempting this for your gate or service exams, which is an MCQ type, so there, the quickness is of importance. So what I would suggest is you remember the step response for your underdamped system, and the equation is something like this. We just derived this equation previously. So I'm going to just put that equation here. I'm just going to plug in these values because I know my omega n, I know my zeta, then I can easily find my omega d, and then I know what is my theta, right? Theta is given by tan inverse of, I can write theta to be in form of sine inverse, cos inverse, or tan inverse. So that's going to be tan inverse of the root of 1 minus zeta square by zeta. So I can just plug in these values, and then I can see which is the closest matching multiple choice answers to this question. Understood? So that is how I solve this question using a shortcut method. So that is how I solved this question using a shortcut method. Now let us see the long steps or the long procedures where you take multiple these things. What do you call? You take, you need to show the multiple steps in your exams, because your exam says it's a 10-mark question. So the long method is to start with the partial fraction expansion, find the partial fraction coefficients, and then convert that into a inverse compatible form, and then take the inverse Laplace transform, and then you get the output. So you have to follow these steps. So the first steps would be to put my R of s to be 1 by s because it's a step response. So once I do that, then I'm doing the partial fraction expansion because it's a non-factorizable term, non-factorizable polynomial. So I get my bs plus c, and that is gonna look like this: a by s plus bs plus c divided by s square plus 12s plus 100. Next is I am multiplying my LHS and RHS with the denominator of the LHS, and that's gonna convert my fractional terms into a equation form, right? So I'm going to get rid of the fractions when I do this, and then I have a just normal non-fractional equation, and I can solve them by equating the powers of s square, s to the power of 1, and s to the power of. So the steps are pretty much the same on how you solve the partial fraction expansion and compute the values of a, b, and c. So by now you should be very thorough with these steps, but nevertheless I write these for every question so that you get repetitive learning. So when you see this over and over, so it just registers in your head and you never and it never leaves your head. So you remember it for your exams and you remember it wherever you do these questions or you use them. So that's the idea. So let's do this and get our ABC values. Then once we have the ABC, then what do? We need to, yeah, we need to find whether we can take the inverse directly or not. So that is your inverse compatibility check. So just let's assume we are not able to take the inverse directly, then what do we do? So we need to make some substitutions or and alterations like what we did in the previous derivation so that we bring it to that form where we can apply the Laplace formula and get the output. Good. So that is your this one. So now I'm putting these values a plus bs plus c divided by good, and that is going to be a square plus b square. So how do I convert that? So what I would suggest is on a numerical question, I'm going to lock on to this 12s. So I'm going to lock to this 12s. And when I do that, so when I lock to this 12s, what I'm going to do is I'm going to take that to be my, how do I get my 12s? When I do s plus 6 the whole square. So which means my a is going to be s obviously. So I can write it in this form, and then my rest of the term is going to be my 100 is going to be split into 64 plus 36. So which means my b is 64, b square is 64, or that is going to be my 8 square. Alright, so I've just done this alternate substitution and I've solved it, and then my 6 divided by s plus 6 the whole square. So now I can apply, yes, I can apply by when I do this into 8 by 8, now I can apply both the forms. So my s plus a divided by s plus a the whole square plus b square, it becomes e to the power of minus at cos bt. Then b divided by s plus a the whole square plus b square gives e to the power of minus at sine bt. Good. So that is your form. Okay. This is your step response. Thank you.